The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone. Thank you for joining us today for our webinar. Before we get started, we're just going to take a few minutes. There are still a few people waiting to join us, so we'll give them a few minutes to get settled. In the meantime, if you weren't aware, this is actually our fourth webinar presentation of our spring series. If you missed any of the previous webinars, you can still watch them anytime on our website at curlinlighting.com. Just a few more people jumping on here. We'll give them another second or two. And I think we are good to go. Well, thank you again. My name is David Brick. I'm the Western Regional Sales Manager at Curlin. I'm joined here today with Amanda Shaneman, our Marketing Director, and we're going to present this webinar entitled MRI Lighting, Evolving with Technology. So let's start the presentation with this question. What is an MRI and how does it work? An MRI, if you didn't know this, is actually short for magnetic resonance imaging, and it's a medical procedure that creates images of soft tissue. So if you have a broken leg, you would get an X-ray, whereas if you had ligament damage or even worse, a brain tumor, you'd get an MRI. An MRI can also help in the diagnosis of multiple sclerosis, tumors, cysts, tendinitis, herniated discs, and various other infections. It was Dr. Damadian that created the very first whole-body human scanner in May of 1977. They named the system Indomitable. The images produced by this MRI scanner were significantly more detailed than those produced by X-ray and CAT scanners. By the end of 1978, Dr. Damadian had founded his MRI scanner manufacturing company called Phonar. It was about 6 years later the device was approved for use by the FDA. MRI field strength is measured in Tesla, which is a unit of magnetic flux density named after Nikola Tesla. 1 Tesla is equivalent to 30,000 times the Earth's magnetic field. Today, 1.5 Tesla is the most common strength of MRI you'll find, but the current standard is now twice that power at 3 Tesla, which can provide better signal-to-noise ratios and higher resolution images. Now, these machines are not cheap. It costs close to $3 million to install a new 3T MRI along with the surrounding suite. But these MRI suites are also big revenue generators for the hospital, with the average scan for an MRI costing over $2,600. So how does an MRI work? The MRI scanner works by combining a very strong magnetic field with pulsed radio frequency waves. The magnetic field affects the protons in your body and causes them to align with one another. Then the RF pulse, which is actually introduced by the imaging technician in the control room, causes these protons to break out of alignment and then fall back into alignment. That movement releases energy, which is measured and used to create the images. The time it takes for the protons to realign with the magnetic field, as well as the amount of energy released, changes depending on the environment and the chemical nature of the molecules. Physicians are then able to tell the difference between various types of tissue based on these magnetic properties. Sometimes contrast agents, often containing the element of gadolinium, might be given to a patient intravenously before or during the MRI, which will help increase the speed at which protons realign with the magnetic field. The faster these protons realign, the brighter the image.
Now that we've covered how MRIs work, let's talk about what makes MRI lighting fundamentally different from standard healthcare lighting. There are 4 non-negotiables in MRI lighting. First, DC power only. Second, non-ferromagnetic materials only. Third, the room must be fully shielded. And fourth, every penetration into that shield must be properly filtered. If any one of these elements is wrong, you risk image distortion, safety hazards, or both. This isn't a space where you can just adopt a standard fixture or grab one off the shelf from your local hardware store and hope for the best. Let's first talk about power for a minute. Alternating current, or AC, which is what we use everywhere else, has a sinusoidal wave pattern. In MRI environments, though, that wave pattern behaves like a low-frequency RF noise. The signal disrupts the imaging process by knocking some of those protons David was talking about out of alignment with the magnetic field of the MRI, and it creates artifacts or graininess within the image that's produced, and it can inhibit the radiologist's ability to accurately determine issues, and it must not be used inside the MRI suite. Direct current, on the other hand, or DC, is clean, it's constant. It doesn't disturb the MRI's RF pulse. This is why MRI lighting systems rely on remote drivers located outside of the shielding space, converting AC power to DC before the power enters the room. It's not a preference, it's a requirement here. The missile effect is always one of my favorite things to talk about, and this is where safety becomes very real. That magnet in an MRI machine is always on. Any ferromagnetic object brought into that room can become a projectile. This is what we call missile effect. If you get bored over lunch one day, Google it because there's so many photos to look at. Light fixtures inside of the magnetic room must be completely non-ferrous, so no steel, no copper, no magnetic fasteners, no little one screw you forgot to change out to something that's non-magnetic. No components that could be attracted to this magnet can be in the room. It's not about performance, it's about protecting patients and staff and ensuring that you don't have this problem moving forward. The magnet is superconductive and maintained with liquid helium. So that is why there's no simple off switch and why that magnet is always on. In an emergency, there's a big red button near the door, typically labeled magnet stop or emergency rundown. It initiates a controlled quench and turns off the MRI machine, which is costly, $50,000 or more, and it's disruptive, 6 or more weeks of your machine being down. Basically, all of that liquid helium is no longer being supercooled, and it is released in a big cloud of helium like you see in this image here, and it will shut down an MRI suite for a very long time. So the assumption in an MRI design is this: the magnet's always energized, and everything installed in the room must be designed around that reality. MRI suites themselves are essentially a room within a room. They're fully wrapped in copper shielding to prevent RF noise from entering and to prevent that magnetic field from affecting surrounding equipment like the technologist's computers. Every penetration through that shield, doors, windows, lighting, power, controls, become a critical coordination point and must be filtered to block the RFI or EMI from entering the suite. Electrical wires, for instance, make excellent antenna. Because of that shielding, every electrical penetration requires filtering. RFI and EMI filters are mounted directly to the copper shield. For a 1.5 Tesla magnet, you're looking at a minimum of about 70 decibels of filtering. For a 3 Tesla or above, that requirement is going to just creep up. These filters ensure that electrical noise doesn't enter the suite and compromise image quality. And space on that shield is limited, so compact, lightweight, multi-channel filtering solutions are strongly preferred. Beyond safety and shielding, we still have to meet lighting performance requirements. IES recommendations for MRI spaces differentiate between the patient transfer zone and the general room perimeter. You're going to need a higher light level during patient positioning and dramatically lower light levels during the scan itself. The question that we always get asked is, why is there so much light needed on that patient transfer table, or zone 1 in this case? For one thing, there needs to be sufficient light for the MRI technician or staff to administer an IV of anything that's needed for the scan. And second, there needs to be sufficient light in case the panic has trauma during the MRI procedure, such as a seizure, a panic attack, or even worse, a heart attack. It needs to be quickly removed from the MRI machine and attended to. Those light levels have to be there for those emergencies.
Now let's take a look at what MRI lighting looked like in the early days and how it has evolved. MRIs from 1970 to 1999 used incandescent lighting, which had limited fixture options and produced poor light quality. The reason fixture options were limited was because standard light fixtures contained ferromagnetic materials. Remember Amanda's slide with the missile effect? That's a no-no. The other problem was that the magnetic field would cause incandescent bulbs to fail even sooner, as the filament of the bulb was ferrous. This led to higher maintenance costs due to constantly changing out the light bulbs. LED for MRIs were introduced in the early 2000s and were a great technological step up for the MRI suite lighting system. They're non-ferrous by nature, have a very long lifetime, they use less energy, and they dim very well. Another benefit with LED lighting is that they don't emit any excess heat into the room, which helps keep the magnet cooler. In 2020, we saw the MRI lighting focus shift from technological requirements to a patient-centered design. LED controls could now dim light levels down to 1% or less when the MRI scan was in process, which helps create a more relaxing and comfortable experience for the patient. LED lit scenic image panels in the ceiling and RGBW technology, often referred to as dynamic lighting, started to become common lighting design for the MRI suite.
So up to this point, we've talked about safety, shielding, and technical performance. But modern MRI lighting isn't just about not interfering with the magnet, it's also about what the patient experiences inside that room. So for anyone who's never gotten an MRI, MRI anxiety is very real. Research shows that 66% of patients experience some level of anxiety during an MRI. A third report moderate to severe anxiety, and up to 10% of scans are stopped early due to that anxiety and/or claustrophobia. This isn't just a comfort issue, it's a workflow issue. It's revenue, it's clinical quality, but patients are placed in this narrow tube, you can see it on the screen here, often for 30 to 60 minutes in a loud environment. You're unable to move, and you just kind of have to sit there. If we're honest, it's not designed to feel calming. So the question becomes, what can we control in that environment? And lighting is one of the few tools in that room that can actively change the emotional tone of the space. There is a growing research around how color and light influence physiological responses. Cool tones, so the blues, greens, soft purples, tend to reduce heart rate and lower perceived stress. Warm ambers can also create a sense of comfort and security. Natural daylight simulation has been shown to reduce the stress hormones and support a sense of normalcy. And dynamic changes, slow transitions, subtle movement, can provide a positive distraction. Clinical benefits that have been observed is shorter patient transit times, reduced sedation needs, fewer falls, less patient movement during scans, higher aftercare satisfaction scores, and improved technologist satisfaction. This isn't about turning an MRI room into a nightclub. It's about using color intentionally. Soft, controlled, clinically appropriate palettes that reduced arousal instead of increasing it. The key here is adaptability, not one fixed color, but the ability to adjust those colors. You can be able to then change it throughout the entire scene and make that something that they can focus on instead of the scary scan that's going on. If you want more on the science of color theory and you missed our webinar on it last week, feel free to check out the replay on our website. But one of the more effective strategies is simply giving patients a sense of control. So before the scan starts, technologists can ask, would you prefer something calming and blue, something warmer, or what's your favorite color? These small moments of agencies can significantly reduce anxiety. Smooth transitions are also important. If you have abrupt lighting shifts, they can feel jarring, especially in that heightened emotional state. Adaptable lighting is particularly valuable for pediatric patients, neurodivergent patients, and individuals who are already highly anxious. Because the system is controlled outside of the magnet room, technologists can make subtle adjustments during the scan if needed without compromising safety. But lighting, as we all know, works best when it's layered. So starting with the ambient lighting that sets the tone of the room. So having white ambient light throughout the space, having the task lighting that supports staff during positioning and transfers, but also making sure that those lights are not directly located over the patient table to reduce glare in patients' eyes while they're getting prepped. Color changing lights can add calm and distraction, and decorative elements, those scenic panels and sky imagery, add visual interest and biophilic design elements. When you combine the soft ambient illumination, adaptable color, and nature-inspired elements, you're no longer designing just a technical room, you're designing an experience. And that experience can directly influence whether a scan is completed successfully. And this project, Methodist Texan MRI Suite, actually does a really good job of making the environment feel healing and not clinical.
So how do we put all this together, and what is required to make it work flawlessly? Well, it takes a turnkey system. Every MRI lighting system requires 3 primary components. The lighting fixtures, which of course are mounted inside of the MRI space. The remote power supplies or drivers that are typically located in the mechanical room adjacent to the MRI suite. And the EMI RFI filters, which are mounted directly to the copper shield wall, which separates the MRI suite from the outside rooms. Remote drivers provide low voltage DC current, which is class 2 output to the fixtures inside the suite. This typically means that no conduit is required between the driver and the fixture in most jurisdictions. Remote drivers should have full range dimming down to at least 1% on the low end to ensure that lights can be dimmed low enough for a patient to be comfortable on the table during the scan. These drivers are typically located in the electrical room next to the MRI suite in a remote protected driver cabinet. From the driver cabinet, circuits enter the shielded room through RFI EMI filters. The filters allow clean lighting power to be delivered into the suite by filtering out any RFI or EMI interference from the electrical circuits that enter the suite. These filters provide varying levels of protection, which is measured in decibels. A 1.5 Tesla machine requires a minimum of 70 decibels filtering, while a 3 Tesla or a 7 Tesla machine would require 100 decibels of filtering. Because the filters are mounted directly to the MRI shield, small and lightweight filters are preferred. Some filters provide multiple channels through a single filter, which mitigates the need for as many openings in the shield. The rule of thumb is the fewer perforations in the shield, the better. RFI filters are extremely important to the proper noise-free operation of lighting in the MRI suite and can often be where things go wrong. This is typically why it is best to use a lighting company that can provide an entire turnkey system for the MRI suite instead of piecing together a system with multiple lighting manufacturers. The MRI suite is usually located in the middle of the hospital floor and typically has no windows to the outside. Emergency lighting is a must, and generator power is often at a premium in hospitals when it even exists. In this case, a single mini inverter could be used to supply battery backup power to the remote driver cabinet. These inverters are usually located in the equipment room along with the remote driver cabinets.
So we've looked at where MRI lighting started and where we are today. So now let's talk about where it's headed and why that matters beyond aesthetics. When we talk about the MRI lighting evolution, it's easy to focus on color and experience, but there's a very real operational and financial case behind it as well. From a financial standpoint, reducing patient anxiety can directly impact sedation rates. Right now, about 6% of patients currently require it. Fewer sedation scans mean lower medication costs, less staffing strain, and fewer recovery resources. Fewer failed scans and reschedules mean better throughput. And when an MRI machine costs over $2 million and generates thousands per scan, throughput matters. There's also patient satisfaction. Imaging is often one of the most anxiety-inducing parts of a hospital visit. If the experience feels calm and thoughtful, that will affect the overall perception of care. From a quality standpoint, calmer patients move less. Less movement means fewer artifacts and fewer repeat scans. It also improves staff satisfaction. Those working in a well-designed environment instead of a harsh and sterile one feel the difference every day. So the ROI here isn't just energy savings, it's workflow, quality, and reputation. MRI suites are some of the most expensive rooms in the hospital. Between that magnet, the shielding, the build out, it's not a space anyone wants to reopen in 5 or 7 years because the lighting system became obsolete. So when we're talking about longevity here, we're not just talking about LED life. We're talking about system life. That means remote drivers located outside the shield where they can actually be accessed and serviced, means upgradable components so that the controls and technology can evolve without compromising the integrity of the room. And it means engineering the system so you're not cutting into copper shielding because a driver failed inside the magnet room. At Curlin, we back that up with our 25-year legacy support guarantee. We commit to long-term parts and service support because healthcare facilities operate on decades-long timelines, and MRI rooms demand that level of commitment. We also provide our maintenance level ratings on our systems and our fixtures. This gives specifiers and facility teams clarity up front about the serviceability, how accessible components are, what the maintenance realistically looks like, how much of a disruption is going to be required if something needs attention. In MRI environments, longevity is strategic. It protects the magnet, the shielded room, and the operational continuity of the department. And when you design from longevity from day one, you're not just solving today's problem, you're setting the foundation for what comes next. Which brings us to where MRI lighting is headed. The market outlook for MRIs is about 8.5% annual growth rate for at least the next 5 years, and that's going to be driven by the patient experience focus. When we look ahead, MRI lighting is becoming more integrated, more intelligent, and more intentional. It's no longer just about meeting safety requirements. It's about how lighting actively participates in the healthcare ecosystem. We're seeing integration with patient records, where lighting scenes can be tied to patient preferences or clinical protocols. We're seeing circadian-informed strategies in imaging departments that operate 24 hours a day, 7 days a week, supporting both the patients and the staff who are working overnight hours. Wireless control systems are reducing penetrations in the shield and simplifying coordination. And predictive maintenance through connected systems means facilities can identify issues before they disrupt scans. But the bigger shift isn't technological, it's philosophical. MRI lighting is moving from compliant to strategic, from something that simply doesn't interfere to something that actively improves the space. And when lighting supports safety, patient comfort, operational efficiency, and long-term adaptability all at once, it becomes a meaningful part of the MRI suite, not just an accessory or a checklist item. So if there's only a couple of things to remember from this webinar, it's this. One is that MRI lighting is not standard lighting in a special room. It's a specialized system inside of one of the most technically demanding environments in healthcare. Fundamental lighting is fundamentally different. It requires that non-ferromagnetic construction, DC power, shielding coordination, and proper filtering. This is not a standard lighting application. Second, modern solutions don't force a trade-off between safety and experience. We can design systems that fully protect image integrity while also supporting patient comfort. Third, adaptable and color-changing technologies aren't just aesthetic upgrades. They directly impact anxiety levels, scan completion rates, and overall patient perception of care. And finally, the right MRI lighting is engineered as a complete system. It's a long-term solution. From remote drivers and filtering to maintenance strategy and legacy support, it's about protecting the magnet, the room, and the investment for decades. When lighting is designed intentionally, it becomes a strategic part of the MRI suite, not just something that fills the ceiling. And with that, we'll take any questions.
All right. If you have any questions, for those of you who have not been on one of our webinars before, you can go to the questions section of the GoToWebinar control panel on probably your right side of the screen and type it in, and they will make their way over to me. I'm going to assume that I need the Curlin website up for some of these questions, so I have it up here just in case that's true. One of the things that I will mention is that we have gotten questions in the past about CT scan rooms and X-ray rooms and whether they have the same stringent requirements as MRI suites. And they do not have the exact same requirements simply because the CT scan room and the X-ray rooms are not giant magnets. So the MRI is just basically a giant magnet, whereas the other rooms are less, they don't have the magnet. So they don't have to be non-ferromagnetic. They don't typically have to be filtered, things like that. But we have also seen where there are some facilities that do use MRI lighting in those spaces simply because they want the technician that can do multiple different types of scans to be able to control the lights the same and have it be the same workflow. So while it's not necessarily required, and if you did it, you wouldn't have to use the filtering that goes through it, you can use MRI lighting in those CT scans and X-ray rooms. It's just not absolutely necessary to do so. Whereas in the MRI, it is 100% necessary to use specific MRI lighting. And the aspect to have it be all one turnkey system is really important as well, just because that way you don't have to worry about any questions between a driver and a filter, and it filters out the controls or something like that, to where you have to figure out where in the line there's an issue and then whose fault it is. With the Curlin system, it is a true turnkey solution to where you don't have to worry about whether the driver is going to work with a filter, whether it's going to work with the controls. All of that has already been tested for you, and it's very simple, so you don't have to worry about it. If you want to figure out exactly what parts and pieces you need for an MRI system, you can actually go to our solutions tab. And in here, we built a MRI configurator for you guys to use. It's very simple. You put the project name in, your room, the different zones, whether it's color changing or static white, and then you add the different fixtures. You can add a fixture type, the fixture number, so a 2500 lumen downlight, your quantity, and then you can actually configure it to where you get like a PDF that has the different number of drivers, cabinets, and filters needed for the project. So that is something that you absolutely have at your disposal. We also have one for our scenic images if you want to specifically affect your images as well. So those are all things that are available at your fingertips. If you have questions on those, please feel free to reach out to us or to the regionals. We'd be happy to help out with that. Next question is, do you have case studies on your previous installations? We do have some images in our image gallery. So if you go to our website on the Learn and Inspire tab, we do have healthcare projects where we do have write-ups. So this is the Methodist Texan hospital that we talked about here, and it shows a image. If there's multiple images, it'll show multiple. We just have one of this suite, and it talks about what all was used, necessarily sometimes why it was used, different things like that. So there are a bunch of MRIs on our gallery post. We also have obviously some other options and other fixtures and case studies as well. So we have a bunch of different versions on this website, and we are always adding more to the website. So keep your eye out for new ones for that. The next question I have is, how does DMX work for Curlin RGBW lights? I'm guessing you're talking about our downlights and our linears for that. And so you can actually, I'm just going to go to our linear because that's easy. So you can actually see it here. So our installation instructions, but our spec sheet shows it as well, I believe. Our color changing solutions are plug and play. So it's actually an RJ45 cable that is included, going from the fixture to what we call a power distribution box that connects to the filtering. So it's very simple. You don't have to worry about having a DMX licensed contractor coming out and trying to work with a whole bunch of wires in an MRI suite and making sure you don't screw it up. It's pre-commissioned, so the controller that comes with the system is already pre-programmed with 8 different scenes to make it really simple and easy for you to be able to include them in your project. So if you have more questions, we also have, if you click on that picture images on our website, we have our spec sheets, our installation sheets, all of that is available on the website. All right. The next question I've got coming in, it looks like, is what's the maximum distance you can put a driver? And that's a great question. For most things, we can actually run it quite far. So for our static white downlights, you can actually run it about 200 feet if you need to. But typically, like David showed in a little picture on the PowerPoint, the cabinets are located right next to it. So our color changing fixtures are about 35 feet just because of the more complex DMX and voltage drop and things like that. But MRI suites aren't huge, and they tend to have an electrical room right next to it, and that is kind of where all of the drivers tend to be placed and the filters that go straight into that MRI suite is installed. Looking at the time, I am going to make one more plug. This is the last of our 4 webinar series of the winter of 2026. If you would like to catch any of our other webinars from this year or previous years past, we would love to have you check those out when about tomorrow and a day, give or take, maybe Monday morning. There, under our Learn and Inspire tab, there is a section called Webinar Replays, and you'll be able to see all of our previous webinars that we've done, including lighting for neurodivergence, behavioral health, women's healthcare, a whole bunch of different ones that we've done throughout the years. You are welcome to watch any of those. And again, our new ones will be on there here by Monday morning. So if you want to watch any of the other ones, you're welcome to do so on that. We do have one more session this afternoon, so if you have other people in your office that would like to watch this one, please feel free to forward that information to them as well. So otherwise, thank you so much. We really appreciate you guys coming today, and I hope you have a great rest of your day and a great weekend. Thank you guys so much.